Today we're going to do a crash course on PySpark, which is the Python library for working with Apache Spark, which is a distributed computing engine for large-scale data processing. So to put it simply, if you have a lot of stuff that you want to do and you don't want to do it on a single machine, you want to split up the work across different nodes, you can do that with Spark, and PySpark is the Python interface to work with Spark. And my goal with this crash course today, as always, is to condense a lot of information into a short amount of time, to go quite deep. In about an hour, we're going to cover a lot. We're going to start with some theory, so what is happening behind the scenes, how does Spark work, what is an RDD, what is a data frame. We're going to cover some terminology like driver, executor, master, worker, lazy transformations, and so on. And then we're going to jump right into the practical part. We're going to use Docker Compose to simulate a setup with multiple workers. We're going to have one master node, 4 worker nodes, and then we're going to run examples. Now, the goal of these examples is not to cover every function and transformation. For this, you can use the docs. We're going to focus on different use cases and different ways of working with PySpark. For example, we're going to build an ETL pipeline, which means extract, transform, and load. We're going to take data from an S3 bucket. We're going to process it in a distributed way, and then we're going to put it back into the same bucket. You could also, of course, put it back into a different data source. That would be an ETL example. We're going to compare the high-level DataFrame API, which is simple and intuitive, to the more low-level way of working with RDDs directly, where we have to express everything in primitive operations like map, filter, and reduce. Then we're also going to go through a streaming example, so where data streams flow in and we process them in real time. And finally, we're going to also take a look at a distributed machine learning training example. So we're going to train a logistic regression classifier across multiple nodes using PySpark. So as you can see, we're going to cover quite a lot today. If you like this video and if you get value out of it, let me know by hitting a like button and subscribing. And now let us get right into it. Alright, so we're going to do a crash course on PySpark today. As always, my crash courses are optimized for speed and simplicity, so we're going to cover a lot in a short amount of time, which is why we're going to jump right into it. As I said in the introduction, we're going to use Docker Compose to simulate multiple nodes, to have 4 worker nodes and 1 master node. The master is basically the one that assigns all the resources, and the workers contain the executors, which will process the tasks. We're going to talk about this. But what you need to know is you need to choose a PySpark version. I'm going to go with 4.2.0. Depending on when you're watching this, you maybe want to go with a newer version. Certain things might differ. Overall, the concepts are the same. Maybe just certain keyword settings or something are differing. But make sure you use the same version everywhere. And also when we install extensions or when we pass certain flags, you need to make sure that the versions of, for example, the AWS thing that we're going to pass later in the video matches the PySpark version that you're using. But we're going to use Docker Compose, so I'm not going to cover the installation of that. If you're not on Linux, you have this usually in Docker Desktop, so on Windows and Mac, or in Mac, you can also install it via the command line. But Docker Compose either is part of your Docker setup already, or you have to install it in addition to that. As I said, this is not a Docker course, so I'm not going to explain that. There's an installation section here, and here you can find the instructions to install Docker Compose. The basic idea, for those of you who don't know what Docker Compose is, it allows you to manage multiple containers, so I can boot 5 containers at the same time without having to do Docker run for every single one of them. Now, in addition to that, we're also going to work with AWS, so just make sure you have an account because we're going to use an S3 bucket. Of course, if you don't want to follow along actively with everything we're doing here, I would recommend you do, but if you don't want to, you don't have to create an account. But we're going to use an S3 bucket. We're going to store files there. We're going to load them from there, process them, and then also save the result back into the bucket. So this is going to require an account here and some settings that we're going to get into later. But before we do any of that, I want to start with some theory. And for that, I'm going to open up my visualization tool, MyPaint here, and we're going to cover the basic idea of PySpark, or I should say the basic idea of Apache Spark, and PySpark is just the interface for working with it. So very, very simple. The idea is I have a master node, and the master node controls or assigns resources to specific worker nodes. I have worker 1, worker 2, worker 3, worker 4. And the idea is now I have some data set. Maybe this is 50 terabytes of data, very large, and I want to process it across multiple machines, across multiple nodes in this cluster. This can be just because I want to get it done faster or because it's just not viable to do this with one machine. So in reality, these would be actual machines. Now they're just containers on my system. So I'm splitting my RAM and my processing power across different containers. But the idea is I just feed that into, I define a task, I feed that to the master node, and the master node then distributes the workload across the workers. That's the most simple way to put it. We're not going to go super deep, but there is some terminology that you need to understand. The master node is the coordinator. The worker is obviously the node that does the work. But then also we have the driver process. The driver process is basically what's running on the master usually, even though it doesn't have to. It can also run outside. And the executor or executor, depending on how you want to pronounce this, is running on the worker and is actually doing the work. This is just some terminology so you know what we're talking about. And the data itself is split into partitions. So the idea is we can split the data into partitions. So 50 terabytes, I don't know the exact numbers here. This is not going to be important, but if you have 10,000, let's say 10,000 rows of data, you could say that you have 10 partitions with 1,000 rows each, and those are going to be split into tasks. We're going to talk about this later when we get into the query planning, when we analyze the actual thing that is happening behind the scenes. But that is the idea of PySpark, or of Spark in general. You have a coordinator and you have the workers that do the work, and you split the data up into partitions. You process everything, then you gather it together if you want to, and then you store it somewhere depending on what you're doing. You can train models like this. You can process data and store the results like this. You can do many different things. You can also process streams, as we talked about. All of this will be covered here by practical examples. So now let us start with the actual setup and the practical work. For this, I'm going to open up my terminal and navigate to my working directory. In this case, it's going to be my tutorial directory. And here I'm going to create a file called Docker Compose YAML. You can do that in VS Code if you want to. I'm going to do that with NeoVim. So I'm just going to create a file called docker-compose.yaml. And here we're going to define our services, which is going to be the master node or the master service and the full workers. So we're going to say services, and the first one is going to be spark-master. The image is always going to be the same. They're just going to run different commands. So one is going to run the command for starting the master process. The other ones are going to run the worker command. But the image is going to be Apache/Spark and the version you want to use, 4.2.0 in my case. The command is going to be, in this case, /opt/spark/sbin/start-master.sh. And then we're going to also provide an environment variable because we need to be running this in the foreground so the container keeps running. We don't want this to be a daemon, a background process. So we're going to say here spark_daemonize, spark_no daemonize is going to be equal to true. Now, also, we want to map a volume, or actually just a pseudo volume. So we're going to map the current directory here to /app so we can easily submit and pass scripts into this container. And finally, we want to make sure that the ports are mapped. So we have the web UI port, which is 8080. That is to see the current status in the browser, so in the web. And then we have the actual communication channel, which is 7077. That is the port for the actual communication in PySpark or in Spark, so that the workers can communicate with the master and vice versa. That is the master setup. Now for the workers, it's going to be quite similar. We're going to say Spark worker1. That is going to be, as I said, the same image. We're also going to use the same environment variable, but we're going to change the command. So let's copy this here. And the command is just going to be start and then worker.sh. However, here we need to provide also the address of the master because the worker has to register at the master. So we need to say spark : and then we provide the Docker service name because we're in the Docker network. So spark-master, no IP address, no localhost here, port 7077. And then to artificially constrain the workers, so it makes sense to actually distribute the stuff, because if I have all my compute in one worker, it doesn't make sense to distribute the computation. I'm going to say that this one has 2 cores, or cores is 2, and then memory is going to be 1 gigabyte of RAM. And that's going to be the case for all these workers. We're now also going to say depends on, because it's going to depend on the Spark master. But that's basically it. So we're going to copy this now, and we're going to do this 3 more times. I'm just going to paste here 3 times, and we're going to call those worker2, worker3, worker4. That is the setup. If I didn't type anything wrong here, we can now say Docker Compose up. The first time you do this, it's going to pull the image for Apache, Spark, and so on. In my case, now this just starts. And once this is done, you can see here that the workers are being registered. But now you can open up your browser, or we can use the existing window here, and we can go to localhost port 8080. So localhost 8080, this is going to put us into the web UI for the Spark master. So here you can see we have 4 workers that registered themselves with the master. All of them are alive. All of them have 2 cores and 1 gigabyte of RAM, and none of them are being used at the moment because we don't have any task that is running. No application here is running. Now, while all of this is running here in Docker Compose, you can press D to detach. So this moves to the background. We don't have it in the foreground anymore. It's still running. And now we're going to write our first script that we can submit to the master to be processed across the different workers. It doesn't have to be complicated, but I want to introduce you to the DataFrame API. So what I'm going to do here, just so I have auto-completion, is I'm going to say UV init. You don't have to do that if you don't want to, because we're going to run all the scripts in Docker. You don't need to install anything locally. The only reason I'm installing it here, so I have auto-completion. So UV add PySpark is what I do. Then I do source venv bin activate, just so I have the auto-completion in NeoVim. If you don't want that, no reason to do that. And then we're going to create now example1.py. And in this example1.py, we're going to talk about the DataFrame API, which is running on something called PySpark SQL or Spark SQL. It isn't because we're connecting to a database. It also isn't because we're writing SQL, but the whole philosophy, the whole under the hood engine is similar to that of databases. So we have query planning and everything. And this is an abstraction of so-called RDD. So maybe very briefly here as a visualization, even though I'm not going to really draw a lot, we have RDDs and we have data frames. And RDDs are low level. So they're very simple. They are resilient, distributed data sets. This is what RDD stands for. And the idea is that they have something called their lineage, which describes how they came into existence. So they are distributed, and the moment you lose them, you can reproduce them by just going through the steps that were used to create the RDDs. And if you want to work with RDDs directly, which we're going to do later in this video, you can only use very simple low-level operations like filter, like map, like reduce. And with data frames, you're using the PySpark SQL API or the DataFrame API, and you have stuff like query planning, and you have optimizations, and everything is very high level and intuitive and simple. This is now just the breakdown, the very, very simple breakdown. RDDs are the low-level objects. Data frames are built on top of them, but also have optimizations, query planning, and everything. And the syntax is much more easy to work with. We're going to take a look at this later on when we compare the same task in different ways of writing them. But for now, let us take a look at how to work with data frames in PySpark. For this, we're going to start by saying from PySpark.sql import the Spark session. This is what is going to connect us to Spark. And we're also going to import row because we're going to craft our data frame here directly in code. We're not going to load it from a file. We're not going to load it from another data source. We're going to define it row by row as a simple first use case. So the first thing is here Spark is equal to Spark session, and here it uses the builder pattern. So we're going to say .builder .get or create. This is going to return the session that we're going to work with. Now we can define a simple data frame. We can say df is equal to Spark and then create data frame, and as input here we're just going to provide rows, stuff like Alice has a certain age. Let's say Alice is 30 years old. Alice has a certain weight. Let's say she has 71 kilograms. Then she has a certain height. Let's say the height is 171, and let's say she is employed equals true. And now we can continue to define rows like this. We can say name is equal to Bob and so on. Now, I'm not going to do this manually. I'm going to copy paste this from my prepared code because I don't want to waste your time here with writing sample data. So here we have Alice, Bob, Charles, Daniel, Ethan, and that's basically it. Some of them are employed, some are not. Some have, they all have different weight and height values. This is a data frame now in Spark. Now, the simplest thing I can do with such a data frame is show it. I can just take a look at it. So for this, I would say df show, and that is already something. This is already called an action here. We can add a comment. This is an action, which means that this triggers something. In this case, we don't have any transformations. We just have the data frame and we show it. So that's not really special. But in PySpark or in Spark in general, we have something called lazy evaluation. So we can filter, we can select, we can group and everything, but it only ever happens really when you call an action, when you take an action. So showing is an action, and there are other actions like writing as well. But before that, you just define what should happen, and it's only executed lazily once you trigger it by an action. So how do we actually run this Python script now in our Docker setup? We have Spark running. Everything is waiting for us. how do we actually submit this Python script to our worker, or to our master, which then can distribute the work to the workers? We do that with a command or a binary that is inside the master container. So we need to say docker compose exec, and we need to do this in the Spark master. There is a script which is located in opt, and then Spark, and then bin, not sbin this time. This is a binary, not a shell script. And then Spark submit. So this submits this script for work to the master. And we need to provide here that the master is still Spark, and then ://Spark master port 7077. And the final argument is then the file that we want to submit. Now for this, we need to map the volume. We already mapped the volume. So now I can say example1.py. Or actually, sorry, we need to say, of course, /app/example1py, because that's how we map the current directory to /app. So that is the script that we're providing here. This script is inside of the container. Now you can see it is being run. If we reload this, you will see that there is, now this finished quite quickly, so we don't see that this is still running, but it finished that quickly because there is a mistake actually. Yeah, because we passed the rows not as a list, but as individual objects. So that needs to change. We need to go into example1py, and that is of course a list of rows, not just rows one after the other. So if you do it like this, we can rerun the same command. Usually it takes a little bit longer, so the only reason it did that this quickly is because there was an error. But now you can see it's running. We can see that cores are being used here, memory is being used here, the workers are working, and then it's done and we can see our data frame. This is just showing it. We didn't do anything. But now we can do other stuff. Like we can say, give me only the name column, and give me only the name column of those that are older than 35, for example. So that would be Bob, Charles, and Daniel. So what I can do is I can go back into example 1, and I can say this time results is equal to df and then select, and I can say I only want to select the name, and then I can say dot filter, and I can say that I'm only interested in the rows where the df age is greater than 35. Now this is all lazy transformation. So lazy transformation here, lazy transformation here, nothing is happening. The only way for something to happen is if I say results.show. This is going to trigger the action that actually does the evaluation of the lazy transformations. So if I run this again, now the output should be a different one. We should just get the names, the 3 names of the people that are above 35 years old. There you go, Bob, Charles, and Daniel. Now, as I said in the introduction, I'm not interested in covering all the different transformations and functions. There's a lot of stuff we can do here. We're going to cover some more, but the goal is not to give you a complete picture of all the different things that you can do here. I want to give you more of a big picture perspective. You can do transformations. I want to show you how to load data from different sources. I want to show you how to store data. I want to show you how to process streaming data, but I'm not going to show you every single function that you can use here. This is something that you can consult the docs for. That is not conceptual, so it would waste time here. But I do want to show you one more thing, which goes quite behind the scenes, low level, I would say. Low level in terms of going quite deep and not just superficially. Is if we do a grouping operation, we have something called a shuffle. And we can also call a function called explain, or named explain, which shows us the physical execution plan. So if I say results is equal to df group by, and I want to group by employment status. So employed is the thing I group by, and then the aggregation is to just give me the average age. So for this, I would have to, first of all, import from PySpark.sql.functions. I would have to import the average function, and then I could do average of h, and then I could also give it here the alias that this is the average age. So we do cover some more functions here, but that whole thing here has a certain results in a certain query plan. So this is how that there's a certain physical plan on how to run this. And again, the actual execution only happens when an action causes it, but we can also take a look at this plan. So I can say results.explain, and in the command line output, I will see the plan of what's happening. And then we're going to briefly take a look at it, and I'm going to explain to you what is happening on a lower level behind the scenes. All right, so first of all, here we have the result, employed, and average age. And if you scroll up a little bit, you will see here the physical plan. And you have to read it from the bottom up. So this is the first action, the second action, And you can see everything is scanned because this is already in memory. We already have the RDD object with all the columns. The first thing we do right away is we project age and employed, which means we drop all the other columns because they're no longer interesting. And here what happens is the group by and the aggregation. And this is a shuffle because what needs to happen is we need to do the partial averages, then we need to shuffle, which means all the samples that belong together need to end up at the same worker so we can do the final aggregation. And I'm going to, of course, give you here again a visual explanation of that because I think it's quite interesting to understand what is happening behind the scenes. So imagine here that you have a data set here, pretty large one. Let's say, just for the sake of simplicity, that's going to be 10,000 rows. And we split this into 10 partitions. And one such partition, let's call it P here, has, of course, 1,000 rows. Now, these rows are rows of people. So we have Alice, and Alice has a certain age, and Alice has a certain employment status and all that. But we have thousands of these rows. And what we want to do is what we just did. We want to group by employment status, true, false, and then we want to get the average age. So if I do that within a partition, this partition, when I apply the partial average here, will result in 2 rows. Why? Because I only have true and false. But I have 10 such partitions, which all end up with 2 rows. So these 2 rows, first of all, have to be partial. So partial averages and not complete averages. So we need to actually store the count and also the sum because, of course, the averages are not just, you cannot just take averages and then throw them together. You need to know, okay, how many people were involved in calculating this average to be able to weigh them properly. So let's say here I end up with true, and true would be a count of, let's say we have 560 people that have employment, and the average age here is 12,050. I'm just making up numbers here. Nothing has to be reasonable. And then I have false, and false could be something like 11,600, for example, and that would, of course, be 440. So these 2 numbers here together, they result in 1,000 rows, and some of them are true, some of them are false. And this is the count, and this is the sum. So, of course, the average is sum divided by count, but we don't do that yet. We only do that partially. And every single partition here results in the same idea. So, of course, different values. So we have partial averages here as well, and these will be different. Here we could have true 12,250, and we could have 490, for example, and so on and so forth. So every single one of these partitions will be put to a worker, and this worker will result or will output 2 rows for the input of 10,000 rows. And what we do now, the shuffle, is we take all the trues, all these triples that are true, and we process them on the same worker. So let's say worker 1. And all the falses are taken to a different worker and processed there. Because then I can do the final aggregation. I can sum up all the sums, I can sum up all the counts, and then I can produce the actual averages. So the final thing we get is also, again, 2 rows, which is our output that we saw in the command line, which is this thing that we're getting in the end. Where is it? There you go. So shuffling, this is another word in the Spark language or another Spark terminology. Shuffling means that we're taking data that belongs together, that has to be processed together for grouping and aggregation, for example, and put it onto the same node. So this was now the very basic example. I want to move on to something more realistic, something more useful, which is working with S3 buckets, with AWS S3 buckets. For this, just log into the console of AWS. If you know how to do it, feel free to also do that with GCP or with Azure or whatever you want to use as a cloud provider. But the idea is I want to have a bucket with data, with large data. Here, we're not going to use super large files. We're going to keep it at 1 gigabyte or 100 megabytes or something like this. But we're going to take this data and we're going to load it partially in a distributed way so the individual workers can only load the part that is interesting to them and can process that. And in the end, we're going to then aggregate everything again or coalesce everything again into one partition, and we're going to put that into an S3 bucket as well. So the only thing you need for that is you need an S3 bucket and a user that can access this S3 bucket and do stuff with it. So just go to S3 here, create a bucket, and we can leave everything as is essentially. So just create this bucket like that. Of course, give it a name. You don't forget that. Let's go with Spark Neural 9 bucket. I'm going to create this bucket here now. And then we just need a user that has full access to the bucket. So we're going to go here to IAM. And in IAM, we're going to create a new user, create user. We're going to call this Spark Neural 9 user. I'm going to say next. We're going to attach policies directly. I'm going to go with S3 full access, which is overkill, but for the sake of simplicity here for the tutorial, we're going to do that. Next, we're going to create the user. That's it. And what you need now is you need to go to that user. You want to go to access key up here, create access key, and you want to copy. First of all, you want to click command line. You want to accept that there's alternatives that are probably more reasonable. You want to go to next. You can describe it if you want to. And what you need now is this access key and this secret access key. Now, I'm not going to show the secret access key, obviously, but what you want to do is you want to create a file called .env. And in this .env file, you want to have two key value pairs. AWS access key ID is equal to something, and then AWS secret access key is equal to something. So the access key ID is the thing that you see here in clear text. This is not sensitive. You can just copy that and paste it here. And then you also want to copy the secret access key, which I'm not going to show here now. You copy this and you paste it down here, and then you save that file. Now, once you have done this, you can close this, and now you have a user that is able to access everything. What we're going to do now is we're going to go back to the S3 bucket, and feel free to put into this bucket whatever you want. In my case now, in my tutorial directory, I have some data sets, which I just generated. These are random data sets. The first one we're going to work with is the people CSV data set. So I'm just going to show you the format. It's really random data I generated with AI. Basically, it has name, age, weight, height, employed, and it has many rows. These are just the first couple of rows, but it just has random names, random weights, random heights, random ages, random employment statuses. That is the data, 1.5 gigabyte roughly. So what we're going to do is we're going to go into that bucket and we're going to upload this data. Now, in my case, I'm going to upload all these files because we're going to need them later, and I'm going to show them to you also. But we're just going to select those, upload those. That's basically it. The other ones are quite simple as well. If we take a look at them, the corpus is just going to have some text later for word counting. And then we have orders and customers. We can take a look at that as well, and we will again later. But orders is basically just showing order IDs with customers and amounts. And customers are same customer ID, but name and country. Not important for you right now. The only thing we care about right now is the people CSV file, because that's going to be our first example. So now everything is uploaded. Upload succeeded, as you can see. Let's go ahead and write example 2, which is going to be loading the data from S3. So we can open up the first file we wrote because we can copy at least this Spark session thing. So I can copy this and I can paste it here without, or actually we can keep the average as well. We don't need the row. So still we create an ordinary Spark session, but we're going to define a path, and this path is going to be an S3 path. So S3A, then colon / the name of the bucket, which I already forgot. It's Spark Neural 9 bucket. So Spark Neural 9 bucket. And then also, of course, /people.csv, the actual file here. And now instead of creating our own data set, we can say df is equal to spark.read.csv, and we can provide the path. So this is going to load the CSV from the S3 bucket. We're going to say header equals true and infer schema equals true. The alternative would be to define the schema manually. This can also save time and be better for performance. It's recommended if you know the schema of the file, but you can also let Spark infer the schema automatically by looking at the file. And now we can do some basic transformation again. Let's say result is equal to something new. df with column allows us to create a new column. Let's create a BMI column, which is just the weight divided by the height divided by 100 squared. So essentially for this, we need the column function here, because that's going to allow us to define expressions using the column. So I can say that the BMI is defined as taking the weight column, then dividing it by taking the height column, and the height column has to be divided by 100 and squared. That is the BMI calculation. Now with column means that the data frame has this column. When I proceed here with the next action, I can access the BMI column. But I'm going to keep it simple. I'm just going to say group by employment status again. So group by employed, and then we can get aggregate average BMI. This will give me just the average BMI per employment status. Probably not very interesting, but that would be something that we can do. And if I want to trigger the execution, I have to say result show. We're going to take a look at how to store this actually in a second here. But one thing is going to be different now because this Python script relies on being able to connect to S3. So I actually need to provide additional flags to my Docker command here. So I still have Docker compose exec master and everything like this. First of all, I of course changed this to example2.py, but also now I need to pass flags for AWS S3. So I need to say -- packages, and the package is org Apache Hadoop, and then Hadoop AWS 3.5.0. This is the compatible version with 4.2.0. If you're using a different version than 4.2.0, you need to figure out which Hadoop AWS package version is compatible with that. So we need to provide this. And then also -- spark jars iv is going to be equal to temp and then .iv2. That is the only thing we need to add. This is so that we can access AWS, but this is not going to work. I can run this and I can also immediately stop this. I just wanted to have the command saved. What we're going to need is we need to provide the .env file as an environment file to Docker Compose. So I need to actually go into the Docker Compose YAML, and in addition to the environment variable here, we're also going to provide an env file. So env file is going to be .env. And this has to be the case for every single one of the workers. That has to be added here as well. And for this to take effect, we also need to say Docker Compose down. That's important because otherwise it will not load the .env file. So we need to actually restart everything. And once everything is removed, we can say Docker Compose up again. We can also say /d to put it directly into the background. And this is now going to load the environment variables, which are our AWS authentication keys or access keys. So now we can run the Docker Compose exec command again, same as before, with the package for Hadoop AWS. This installs everything, as you can see here, downloading, and now it starts executing the work. You can see example2py is running. This is going to pull the data set from AWS S3, process it, and then show the result on screen. You can also see here always that it says which partition, which executor, if you're interested in the details. And there you go. After 52 seconds, we have the results, true, false for employed, and then the average BMI for the respective group. This data was loaded from S3, and now we have the result here. The next step, of course, naturally, is to save the result also back into S3 as a Parquet file, for example. So we can say example2py, and what we need to do instead of showing the result is we need to condense it or to coalesce it back into one partition and to then write it into S3. So we can say here result coalesce number of partitions is going to be 1, then write. The mode is going to be overwrite. So this is going to replace existing files. And then we're going to say .parquet. This is just a format that we want to save this in. And the path is going to be basically the same bucket, but we're going to provide a different directory afterwards. So I'm going to say that I want to use S3A Spark Neural 9 bucket. And then we can say, I don't know, stats output or something like this. So I can now close this and I can just rerun the exact same command. Instead of showing this now, it's going to save this in my bucket. So I can go back to this bucket and I can see that I have certain files in here that I just uploaded, my different data sets. And in 1 minute or so, I will have a directory with a Parquet file in it that will contain the results. So now it's done here in the command line. Let's refresh and we will hopefully see, there you go, stats output. There's a folder and here we have the Parquet file with an odd name. So what we can do is we can just click on it. We can download it, we can save it here in tutorial. Let's call it result.parquet. And then I can just go here, uv add pandas. You didn't see the command now, but uv add pandas just to install pandas. And then we can write a very simple script like, let's call this example2 look.py, look because we're going to look into the data, and then we can say import pandas as PD, and then just print PD, or actually print, PD read Parquet, and the file was result Parquet. That's going to be the script. This is what we're going to run locally actually. So uv run example2 look.py, it was never closed, okay. Even when I write just a single line of code, there might be a typo. And one more thing, I forgot to install this. We need also PyArrow to be able to do that if you want to take a look at this. So uv add PyArrow is going to allow us to read Parquet files. But then you can see here we have employed, true, false, and the average BMI per group. So this would already be a minimal example of an ETL process, of an ETL pipeline, where you have extract, take it from S3, transform in a distributed way, and then load back into S3. That would be an ETL pipeline, a very minimal version of that. Now, what I want to show you here in this example is also how to define or how to create user-defined functions. These are basically things that cannot be expressed, or maybe can be expressed, but you choose to express in your own function instead of using something like group by or average or something like this. It's not recommended. This is like a last resort because it's usually not efficient, but you can define your own functions too. So you can say add UDF, then we can define age group, which takes in age as input and then says if age is less than 30, we can return the string young. So that would be a categorical attribute based on age. And then we can say if you are elif, if you are under 60, we can say middle-aged. I hope you're not offended by this, by the way. And then else would be senior, let's say. That is now age group, a function that I can apply. So what I can do also in addition to BMI is afterwards I can say with column, and the column here could be age group. How do we define that? By calling age group on the column called age. That's going to produce this column age group, and we're going to group then by this column age group. So I'm going to say by age group, and then for each age group I want to have the average BMI. But the most important thing is you add this UDF, user-defined function decorator, onto your function. So we can submit this to like this, just doc compose exec example2 again. Then this is done and we can download the new Parquet file again. Overwrote the old one, and now let me clear first so you can see this. If I say uv run example2 look py, we have the age group and the average BMI per age group. Now next I want to show you a simple example that illustrates the difference between the DataFrame API, which is high level and intuitive, and the low level RDD way of working with data in a distributed way. So for that, we're going to create example3.py. We're going to copy a bit from example2 because the setup is quite similar. We're going to copy this here. So we're still going to connect to the Spark Neural 9 bucket, but this time we're going to load the corpus.txt. So if you don't remember, I showed it before, but the corpus.txt is just random text. You can, of course, use real text, paste whatever you want into this file. It's, I think, roughly 100 megabytes. It just contains some basic words. The idea is to count the words in a distributed way. How you do that with the DataFrame API is quite intuitive. You just go and split the text and count the words. So you load the txt file from AWS, then you say counts is equal to, and then we can use parentheses to be able to do this in multiple lines. And I would like to cover this from the inside out. So first of all, we have a column value. That's going to be our text basically. And what we want to do with this column is we want to split. So we want to apply a split. This, of course, is a function we need to import here. So we're going to need split, we're going to need explode, and of course, we're going to need column. So we want to split the column based on a regular expression. And the regular expression is just going to be \s plus, which means like any number of white spaces and line breaks and tabs and everything, just split on that. That's going to be a word. And as a result of this, we get the word, but we want to get the word on each row. So every word should get its own row. So for that, we're going to say explode. We're going to give that an alias word, and we're going to select that. This is basically how we do this here. Now, of course, we have the same word appearing multiple times as a separate row. So what do? We say group by, and group by is going to be by word. And finally, we just say dot count. This is really as simple as it gets. We split, we explode, so we split it into rows, we group, and we count. That is it. This is our aggregation, the count. Now we just have to display it in an ordered way from the most frequent word to the least frequent word, and we're only going to take a look at the top 20 entries. So we're going to say counts.order by column is going to be the count column, but we're going to do that in descending order. And then we're going to say show 20. Just show me the 20 most frequent words. That is how you do that in a DataFrame API, which you realize you're using by using the SQL functions here. So if you use something from PySpark SQL functions, you're working with the DataFrame API, which is optimizing and high level. So we could do the same thing as before, Docker command, example 3 this time. This will just count the words from this text document in S3. Okay, actually see I have a syntax error because of course I used select, but not dot select. So example 3, we need to say, of course, dot select. And before that, we need to first of all load the data. So spark.read.text. And we need to load the data from the corpus. We didn't do that. So this is the first step, get the data and then select all this. And there you go. We have the most common words, the, be, to, off, and a, in, and so on. So this is, of course, artificially crafted data. You can also try this with real text, but the functionality worked. This is how you do this with the DataFrame API. Let me show you again. Example 3 py. Very simple by just chaining these simple methods or operations or transforms. Now we're going to do the same thing in RDD, with RDD transformations, with the RDD API. So for that, we're only going to copy the initial AWS stuff, so this here, but we're not going to use the functions or the SQL functions. We're going to delete that. This is the only thing we need. And then we can express this in the form of MapReduce transformations. So I'm going to say again counts. I'm going to use parentheses again. This time we're going to load the data directly before we forget that. So spark.spark context and then text file. This is just a different way that we're using here. We're going to pass path. And here now we use flat map. So we're going to take the lines, we're going to map them to individual words. So lambda line will be line.split. This is quite simple. And the general idea of MapReduce, for those of you who don't know about this, I'm going to use my paint again, is that you yield individual tuples or triples or whatever. Or tuples of tuples. So the idea is I encounter a word, let's say the, and what I yield is the 1. So this is a 1. And then I yield it 1. And then maybe another one, the 1. High 1. It 1, whatever. And that is the first state. That is what we call map. I just take the word that I'm currently reading, I'm taking the word that is coming in as input, and I'm returning the 1, or whatever the word is, 1. The reducing then means I take all the ones, or all the sorry, which have a 1, and I just sum them up. So in this case, I would have 3, and I would end up with the 3. This is reduce, this is map. This is the most simple example that you have for MapReduce. And this is what we're doing here exactly in the code. We're just splitting the text, and then we're doing dot map. And what we're mapping is we're saying lambda, if there's a word as input, I return word and 1. And I do that as a tuple here. This word and then 1. And then what I do is I reduce by key. So every word that is the same, if I have a tuple like this, every tuple that has the same first element, that has the same word, I reduce by summing it up. So if I get 2 of these tuples that have the same word, I get their values A and B. So lambda, A and B, which would be 1 and 1. These would return A plus B. And then I can, of course, do that again and again. So then I will get maybe the first time I get the 2. Next time I get the 4, and so on and so forth. I just sum all of this up. I reduce with the sum operation. And then basically to display this, I just have to say counts, take ordered. I'm going to go with the first 20 again. And the key for the ordering, this is now a different way to express this. The key is a lambda expression. I'm getting x is the tuple, and I want to sort by the value. So by the second parameter, or by the second value, which is index 1. So I get x1, but I negate that because I want to have the descending order. This is how you express this in terms of MapReduce. Now let's see if I messed up anything. Otherwise, this should work if I just say run the same command with example 4. And there you go. We get a different format, but we still get the same words with the same counts as tuples. Now, you might be saying that this is not really a huge difference in terms of complexity. So look at this, example 3 and example 4. That's not really much more complicated. It's maybe a different way of thinking. Here we just do split, explode, select, group, and so on. Here we have to think about mapping and reducing. I would say that this is more complex when you get even to this task, because you have to think of yielding and then reducing by key. But you will see the difference, and I'm not going to write this from scratch here, but if I go to example 5 py now, I'm going to copy paste the script that I prepared, which should illustrate something very simple in the DataFrame API. Here what we have is we have the orders CSV and the customer CSV. Let me remind you again what we're doing here by taking a look at the data. We have orders. The orders have an ID, an order ID, and a customer ID. So who did the order, and then the amount, the price of this order. And the customer's CSV is basically just customer ID, which is the same that we have here as the second parameter or the second value. Then we have the name of the customer and the country that the customer is from. Now, what our script does here, the example 5 PY, and I didn't paste it here, or actually I pasted it in a different window. There you go, here it is. What we're doing here is we're loading this from the S3 bucket. Remember, we uploaded it earlier. We have these two data frames. We read them from the CSV file, and then we just join. We just say orders join customer on customer ID. That's a database operation, basically. That's SQL-like writing here. I just say these two have this column in common, join them, group by country, average amount. That's it. Give me the average amount by country, because I'm joining the customer that has the information about the country, the order that has the information about the amount. I'm combining them. I'm just doing a group by operation, and then I'm ordering and showing the result in descending order. This is what I can do in the DataFrame API. The same functionality with the RDD API would look like this. So this here is the same idea, but in a different way. Now we drop the header, that's not really important, but what we do here is we need to think again about mapping and reducing, because what are we doing? We're taking in an order and we're mapping. We have to just yield back customer ID amount for every single one of them. Then for the customers, we do customer ID country. So then we have different yielded objects with amount and with country, and then we have to reduce them together, which we do by joining. So we then end up with customer ID, amount, and country in a tuple of the tuple, or in the second position, we then also have a tuple. And then again, we need to map, because we need to say, okay, for this country now, I need to say, this is the amount, because we're going for the average. So I need to sum up the amount, and I also need to keep track of the count. So I yield the amount and 1 to be counting, and then I reduce. I sum up the count, I sum up the amount, and in the end, I map again by saying country average amount, and then I just display the results. You can see it's not necessarily super complex conceptually if you understand this. You're just yielding values, you're combining these values, but you have to explicitly state how you're going to do it. And it's much more low level and less intuitive, whereas with the other API, you literally just say join group by, that's it. So that would be an example, and the more complex you go, the more you have to write with this syntax, with the API, with the RDD API. We can let this run now, and there you go. When we're done, we see the country and the average amount of the orders. Now we can do the same thing again with example 6, and we also get the same values here, but in a different format, and we expressed the logic in a different way. So next I want to show you an example using streaming. Streaming means you're getting a continuous stream of input, not just one file that you're reading from somewhere, not just one big data set to process, but you continuously receive new information, new content to process. Now, usually in a professional setting, this would be coming from something like Kafka. Here, we're just going to open a socket connection. I'm going to be throwing text into the terminal, and we're going to do the word counting live. So we're going to say now example 7.py, and I'm going to copy a little bit from the example 3, which is our word counting example. I'm going to paste it here again. But this time we're not going to go to S3. We're not going to load anything from there. We're still going to create a session. We're still going to do the counting here, but we're going to also do this slightly differently. So first we're going to define lines up here, which is going to be equal to spark.readstream.format. And that's going to be socket. Option host is going to be localhost. So we're going to read from the same device. And option port is going to be 9999 for the sake of simplicity here. And then finally, we just say .load. So the idea is we're going to run the socket. We're going to listen to localhost, and there we're going to feed in the information. This is super, super trivial, a local example. I just want to show you that Spark can process data that comes in as a stream. Again, as I said, realistically, this would be a Kafka stream or something similar. And then basically, we don't need this anymore. We're just going to say lines.select. So we're going to do select, explode, same as before, group by count, and then just order by here directly afterwards, order by column count descending. We're not going to do show 20. So that's just going to be a one-liner now. And we should also remove this bracket here. And now we're going to write all of this to the output as an output stream every time something changes. So counts.writeStream output mode is going to be complete. Format is going to be console, and then .start.await termination. And the only thing left to do here is to set the log level to warning. Otherwise, we're going to see too much information. So spark.spark context, and it was set log level warn. That is it. So this is going to listen now for text input on port 9999 on localhost. So now we're going to run the same Docker command as before, just this time with example 7py. But before we do that, we're going to run something else. So that's a command I'm going to copy paste here. It's just a simple Python script that lets a socket listen. So for this, go to the same tutorial directory, and we're going to type this docker compose xx sparkmaster 3 python sparkmaster python 3, and then we just have an endless loop here where we can put input into this program, and it's going to just accept and listen on port 9999 in this container. So run this first, then run this script, and then this is going to allow us to process stuff in real time. Actually, to not block with my camera, let's do it like this so you can see everything on the left side here. And basically I can just type something like hi. It takes some time for this to start. First is going to be just batch 0. Batch 1 here is hi. I can say hello world, enter. Then this is going to be sent, and it's going to tell me hi, hello, and world. I can also go to Wikipedia, for example, and just take some, I don't know, let's go with this here. I can just copy this part. I can paste it here, and it's going to give me the word count for all of these words. There you go. Also sorted the off to Colorado. And this is stream processing. So I can constantly, of course not here, but here, I can constantly be typing in new stuff. It's going to count it, and it's going to update this table here. And now finally, I want to show you how we can do distributed training of machine learning models using PySpark. This only works with simple models like logistic regression. We're not going to be able to do this with neural networks or transformer-based architectures, but we can do that easily with logistic regression, which is what we're going to do. As a reminder here, again, we have the people CSV file. We're now just going to train a model that predicts whether a person is employed or not. This data is completely random, so we're not going to get anything interesting, but of course replace this with an iris CSV, with the iris dataset or something, and you will see actually useful results. So we're going to say example8.py. I'm going to copy from example2.py just the loading of the data frame or dataset from AWS S3. For the functions here, we're only going to need the column function, and then we can also close this and save this. So now we have the people CSV file here in the path. And then we can start with loading and pre-processing the data. So data frame is equal to spark.read.csv. That's going to be the path. That's going to be, again, header equals true and infer schema equals true. Then I'm going to say df is equal to df with column, and the column is going to be label. And label is essentially just going to be our employed column, but we're going to typecast it into an integer so that we have a number that we can actually predict, not a Boolean. Then we can do a train test split. Train test is equal to df random split, and we can just provide here 0.8 and 0.2. And from here on, we need the machine learning stuff. So we're going to start by importing from PySpark.ml the pipeline. Then from PySpark.ml.feature, we're going to import the vector assembler and also the standard scaler. So vector assembler basically combines the data into one vector that we can pass. Then from PySpark.ml.classification, we will import the logistic regression, which is our model that we're training. And then from PySpark.ml.evaluation, we can import the binary classification evaluator, because this is a binary classification. Is a person employed or not? So this is the evaluator that we're going to use for that. So the first step in our pipeline will be the assembler. The assembler will take in the features and turn them into one vector. So we're going to say here vector assembler, and then input columns is going to be a list, and we want to use the age, the weight, and the height. The output column will be raw features. And then the scalar is going to be equal to standard scalar, where the input column will be the raw features that we just created with the assembler, and the output column will just be features. That's basically it. So now we have a data frame with label and also with features. So now we need to train a logistic regression model where the features column is going to be features, and the label column is going to be label. And then this entire thing has to be expressed as a pipeline. So pipeline is going to be equal to pipeline, and we're going to pass the stages here. Stages is going to be equal to, first of all, assembler, second of all, scalar, third of all, logistic regression model for the prediction. And then we can just say model is equal to pipeline fit, and we're going to pass the training data. Now to do inference with this model to actually get predictions, we can say predictions is equal to model.transform, and then we pass the test data. So this is going to give us the predictions for the test data, which we can also use again to do evaluation. But if we want to take a look at the data, we can also say predictions.select, and we can select the columns here. So age, weight, height, then the actual label, the true value actually, and also the prediction. And then we can get the first 10 entries just to take a look at it. But then we can also get the area on the curve. So AUC is going to be equal to binary classification evaluator. Label column is going to be equal to label, and then evaluate predictions. And then we can just print AUC like this. Now let's see if this is actually correct or if I made any mistakes or any typos. But before we can actually run this is going to rely on NumPy. We don't have NumPy in the default image. If we take a look at Docker Compose, this image here doesn't have NumPy in it. So what we need to do actually is we need to build using an own Docker file. So we're going to comment out the image everywhere here. We're going to save this and close. We're going to create a Docker file, which is just going to take the image. So we're going to say from Apache Spark 4.2.0. Then we're going to say user root, and we're going to run pip install. So run pip install -- no cache dir numpy, and then user spark. That is our Docker file. And in our Docker Compose now, instead of image, we need to say build this directory here. Build this local directory for all the workers and also for the master. So we're just gonna paste this everywhere here, save this, Docker Compose down, very important, and then Docker Compose up with build. So now Docker Compose up -- build. Everything seems to work. We can press D again to detach, and then we can run our Docker Compose exec again with example 8. So with our machine learning script. And there you go. After a while, we can see on the one hand here the AUC, which doesn't mean a lot in this case because the data is completely random. But also if we scroll up a little bit, we can see our 10 rows for the inference with the prediction and the label, in this case, all positive cases. But this is how you can do distributed machine learning using PySpark. So that's it for this video today. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, in case you're interested, on my website, you will find a services tab and a tutoring tab. There you can contact me if you need help with a project. If you need a freelancer, a consultant, you can contact me via LinkedIn or email at the bottom of both pages. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.